that the last time I did this recording, it looked like I had muted the audio. So I'm going to try this example one last time. So this is the graphing assignment, the last example with the tides at Norris Beach. So I'm going to go through it again here. So it's told to us that the tides at the beach have been measured at a low of 3.8 meters at 2:30 a.m. and a high of 12.1 meters at 9:30 a.m. of the same day. In part A, it says make a graph of the water level at Norris Beach for one day. Now, because we are graphing things at different times of day, we are graphing a 24-hour cycle. I've already counted the squares on the grid, and there are 13 vertical squares and 24 horizontally. So this actually works out really nicely because my maximum height is at 12.1. So I can make my scale basically go up and right by 1. So I'm going to do that right now. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and again, this is 0. So on the vertical, this is measuring height of the water or depth of the water in meters. And on the horizontal, I am looking at time from midnight. So how many hours from midnight? And again, measuring this in hours. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and feel free to skip part of this video. I know it's not as exciting. 20, 22, and 24. Okay, so I have my scale set. And I'm looking at 2 key points that were given to me. So the first thing is that the height is low at 3.8 meters at 2:30 in the morning. 2:30 in the morning is 2.5 hours after midnight. So I'm going in here somewhere between 2 and 3. Going up to 3.8. This is going to be the start of my graph. I'm going to mark that point. 2.5 hours after midnight, the low is 3.8. Then the high is at 9:30 a.m., so 9.5 hours after midnight, 9.5 hours, and the height is 12.1. So 9.5 hours, height of 12.1. And again, I'm going to write that down, 9.5, 12.1. The next thing I need to know is what is the width of this cycle, meaning how many hours is it between the high and the low? And what I'm going to do is take 9.5 minus 2.5, and that gives me 7 hours. So there is a 7-hour difference between the high and the low. So if I go another 7 hours, I should hit the low again. So what's 9.5 plus 7 is 16.5. So 16.5 hours after midnight, I'm going to hit the low again. So this is going to be 16.5 hours. The low is 3.8, right? That's my minimum value. And I'm going to add 7 again, and that brings me to 23.5 hours. That's going to be the high. 23.5 hours after midnight, I'm going to be back at the high tide at 12.1. You could write your scale in AM and PM if you wanted. So 12 would be noon. This is 2 p.m. This is 4 p.m. You could write it that way as well. I just find it easier because when I'm adding and minusing the hours, it's going to give me a number like 16 and 23, and then I don't have to go back and convert it to AM and PM. So it's just a little bit easier to use the 24-hour clock. Okay, so we use the distance between, or the time between high and low tide to find all of our high and low tides. What we need now is how long is it to the halfway point? So it's going to be somewhere here, right? So the first thing we're going to do is, what is the halfway point? This is going to represent the central axis of the wave, right? The central axis of the wave is represented by the K value when we are doing our transformation equation, right? And to find the midline, the middle of the wave, we have to take our min plus our max divided by 2, essentially take the average. So 12.1 plus 3.8 divided by 2. I'm going to throw that into my calculator here. Divided by 2. My K value is 7.95. And this represents the middle height of the wave. So it's going to be very close to 8. Now what I need to know is, what's the time? What's the time between the high and the low? We know that the total time is 7 hours. So halfway is going to be 3.5 hours. So 3.5 hours after 2.5, I'm going to have a middle height of 7.95, which I got down here. So I'm going to take 2.5, I add 3.5. That says 6 hours. 6 hours after midnight, I am going to be at halfway between high and low tide. So 6 hours, 7.95. I'm going to write that as a coordinate. 7.95. Okay, so here is my high, there is my low, and now I have enough information to kind of keep going and finish the rest of the graph. I go to the high, 9.5 hours. I add 3.5 hours. That brings me to 13. So at 13 is my next middle. And 13 plus 3.5 brings me to 16.5, which is what I'm expecting. I add another 3.5, brings me to 20. And there we go. So this is 15, 7.95, and this is 20, 7.95. So now I have the tops of the graph and the bottoms of the graph, and we can kind of sketch in the rest of the graph here. So this is the representation of the depth of the water throughout one day. So part A, done. Part B is saying, write one sine and one cosine equation to represent the flow of the tide. And hopefully you can see that this is a symmetric wave that continues for on and on and on. So you can go forever. You could start at the beginning here and notice that this looks like a bell curve, which is a negative cosine. You could also notice that you could start at the middle, go up and then down, and this would represent a sine wave. Or you can start at the top, go down and back to the top, and that would represent a positive cosine because it's the same shape as the original, right? It's in that bowl shape, top to top. Or you can start at the next middle, go down, and this would be a negative sine wave. So there's lots of ways you could look at it and graph any of these 4 functions. I'm going to just graph the first 2. So I'm going to write the equation for the yellow, and I'm going to write the equation for the blue. And if you want to practice your skills, you can write the equation for green and purple. Some things to remember when we're writing trig equations. The amplitude is going to be the same for any of these equations, because we're not changing what the graph looks like. We're just changing how we write the equation. But all of the equations that we write have to make the same picture. Okay, so the amplitude, the height of the wave, the maximum value, is going to be the same for all of our equations. And just a reminder, this is how we find amplitude. So 12.1 minus 3.8 all divided by 2. I believe this is going to give me 4.15. I'm just going to double check on my calculator. I did this earlier today. There we go. So my amplitude is 4.5. My K value I already found. And remember, what does K represent? K represents where the center of my wave is. So no matter what equation I use, the center of my wave is the same. So A and K are the same. I'm going to keep those in 2 boxes. What else is the same between all the different parts of the wave? The next thing that's going to be the same is the length from the beginning of one wave and the end of the next, right? They're all going to be the same wavelength apart because we are graphing the tide. So no matter how we write the equation, it should give us the same picture. So no matter what equation we write, we have to have the same period. We know that it was 7 hours from high to low. So to come back to low again, it's 14 hours. So to find our B value, we take 2 pi and divide it by the period that we see. We see the length of the period to be 14 hours. So I'm just going to reduce this fraction. My B value is going to be pi by 7. So these 3 values do not change. What does change is whether you are graphing a positive or negative cosine, and where does the graph begin. So you'll notice on all 4 of my highlighted waves, they start at a different point. So your H value will change, and whether or not your A value is positive or negative will change, but all others will stay the same. So let's look at the yellow. If I'm writing the equation for the yellow function, it is a bell curve. So it's a negative cosine. Negative 4.15 cosine pi by 7 t minus, where does the yellow graph start on the x-axis? It starts at 2.5 hours. So 2.5 plus 7.95, right? The center of the curve. I could also write an equation for the green graph. And actually, I'm going to change this y and I'm going to make it h. The height of the water depends on time. I could also write the green graph represents a sine function because it goes from middle to middle, and it goes from middle going up, just like the original. So this is going to be a positive 4.15 sine pi by 7 t minus, where does the green wave start? The green wave starts at 6 hours. Oopsie. Oh, I could work on my handwriting here. There we go. Plus 7.95. Right? Now you can even write the equation for the purple and the blue if you wanted to, but it's only asking us for one equation of each, so that's sufficient. Okay, part B, done. And what is the height, what is the tide height at 12:45 p.m.? So to answer C, we have to write this time as hours after midnight. So 12:45 p.m. means 12 hours and 45 minutes after midnight. To write this as a decimal, it will be 12.75, right? Because 45 minutes out of 60 is 75 or 0.75 of an hour. It's 3/4 of an hour. So this is the time I am given, how long after midnight, and I'm asked for the height. So to answer this, you're going to choose which equation you want to work with, whether it's the cosine or the sine wave. It really truly doesn't matter. So to answer C, I'm going to choose the first equation just because it's the first one. I'm going to find the height by using my calculator. and literally typing this equation into my calculator. What's my time? 12.75 minus 2.5 plus 7.95. Oopsie. If you are using a graphing calculator, you can type exactly what I just have here, and it will spit out an answer. If you are using a scientific calculator, you need to specify after you write 4.15 that there's a multiply sign here. And after you write the pi by 7, that there's a multiply sign here. And you need to make sure that you open 2 brackets and then you close 2 brackets. You also need to make sure that your calculator is in radians. Otherwise, you're going to get messed up answers here. Okay, so I'm just going to take a quick moment here, type this into my calculator, pi by 7. Open another bracket, 12.75 minus 2.5, close 2 brackets, 7.95. And it's going to give me that the height of the water is about 8.4 meters at that time. And you can even check on our graph. If we drew a good graph, it should be pretty close to what we see. So let's see, 1245 is kind of here. So let's see, how close is our graph to what we see? 8.4, so this is the 8 line, 8 is right here. So yeah, not too bad, right? We drew a pretty good graph here. Now, D is where it gets a little bit tricky. D is saying, if the boat needs 10 meters of water to dock safely, how many hours of the days is it safe to dock the boat, right? If it's too shallow, the boat will drag on the bottom of the ocean floor and it's going to get real messy. So I'm just going to erase all of my highlighting here so I can identify what is the safety line. The safety line is 10 meters. So what I'm interested in is how many hours is it safe to dock this boat? I'm interested in the length of time between here and here and here and here. That means I need to know what is my X value at this point. It looks like it's going to be 7 or somewhere close to 7. So that's what we're kind of aiming for. And it looks like this will be somewhere in the noon range or somewhere close to 12. We don't know for sure, but we're going to use our equation to solve for it. We're going to use 10 as our height, and we want to work backwards to find the time t. So again, I'm just going to keep using the equation I started with, but instead of h equals, it's now 10 equals negative 4.15 cosine bracket pi by 7 bracket t minus 2.5, close both brackets, plus 7.95. Now what we're going to do is we're going to essentially work backwards to find t. So first thing I'm going to do is minus 7.95 from both sides. 10 minus 7.95, that gives me 2.05 equals negative 4.15 times cosine blah, 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 blah. I'm not going to rewrite the bracket because I'm not going to need it right now. The next thing I'm going to do is I'm going to divide both sides by 4.15 negative. Divide by negative 4.15. This is going to give me the decimal number, 0.493976. I'm going to keep like 5. You should keep at least 5 numbers after the decimal. The reason is, especially if you're using a graphing calculator, you need a lot of decimals to get a halfway decent / accurate answer. If you're using a graphing calculator, it'll remember this number as you keep on working. Some scientific calculators will remember and some won't. So I always make sure to write lots and lots of numbers in case I make a mistake. I don't have to start over. I can just go back and start from the line where I made the mistake. Now, in grade 9 or 10, we had something like this. Cos equals, 5/12 or something, because we had a triangle that was 5 and 12, and we were trying to find this angle. How did we isolate the angle? We used cos inverse, right? Cos inverse 5/12. We're going to use the same idea here as well. Pretend this is just an angle. How do we get rid of the cosine? We use inverse cosine. On your calculators, it will be the second function, 49 ... I don't want to write that number again. So I'm just going to throw this into my calculator. Cos inverse of the number that we found gives me 2.08745 equals this stuff. Okay, so now again, my goal is to get t by itself. So I see that there's this outside multiplying it. So I'm going to multiply by 7 and divide by pi. Times 7 divide by pi. And that's going to give me 4.651198 ... t minus 2.5. So the last step I need to do is just add 2.5. So the time will be 7.15 hours after midnight. Okay, so let me see. If I do 0.5 or 0.15 times 60, that's approximately 7:10 a.m. is when the height of the water is going to be 10 meters. Hey, that's actually really close to what we assumed it would be when we looked at our graph. Yeah, so close to 7. Okay, so that means our graph is a really good picture here. So this point says that at 7.15, the height of the water is 10 meters. In order to find this length here, I need to know what time this is. The way that I do that is by using the idea of symmetry. Symmetry means everything here is symmetric. You can see that there is an arc here. So if I cut this in two and know this length, I can add another piece and I will have the other point. So I'm going to say 9.5 minus 7.15. How many hours is that? That is 2.35 hours, which means this is 2.35 hours. So to find the other point, 7.15 plus 2 times 2.35, this coordinate is at 11.85 and 10. 10 because that was the height I solved for. That was the whole point of it, right? Which is pretty close to where we thought. We said it was going to be near 12. So this convinces me that our graph is actually a really good picture of what's going on in reality. Now, how do I find this point here? Well, I'm going to notice that this is one rotation, and then this is the start of the next rotation. So that means every point on the blue curve is 14 hours away from every point on the purple curve, right? Because when we were looking for our B value, we already calculated that the length of the wave was 14 hours. So that means if I know my original point is 7.15, I'm going to add 14. And this means that this point here is at 21.15 and 10. Now, how many hours is it to the end of the day? Well, I know the end of the day is 24 hours, so 24 minus 2.15. I'm not using symmetry here because you can see that there's only a little bit of that wave left till the end of the day. It's not a full curve, right? So I got to find the difference here. So this little piece is 2.85 hours. Okay, so if the boat needs 10 meters of water to dock safely, how many hours during a single day is it safe to dock? So I'm going to take all the little pieces I found, 2.35 times 2 plus 2.85. So I'm just going to add that into my calculator. 7.55 hours. This is how many hours there are in a day where you can safely dock your boat. And that is the end of your question. And this question is a very good quiz question. Hint, hint, nudge, nudge. Quiz on Monday. Don't forget, it's going to be one question, one page, just like this.